Blake.
I'd love to start.
Yeah, let's do it.
Do you mind doing number 17 on 9.3? Sorry, I couldn't read that number.
That's okay. Sure. All right. So we're looking at 17. Okay. So I would start by dividing both sides by tan x. And then we'll divide both sides by a plus y. I guess we should have written y as dy dx, right? Or y prime as dy dx. Let's do that. So we have that. So I think we're probably good from here to do our integration as we have things separated. So on the right, or on the left, that's like a u sub problem. But since a is a constant, it's like the easiest u sub that's ever u subbed. We end up with just the natural log of a plus y. And then the integral of 1 over tan, or that's the integral of cotangent. And that still doesn't look appealing to me. But if I write that as the cosine over sine, now I think I'm in business. So I'll do a u sub with that. So I'll say u will be sine. So du is going to be cosine x dx. So really, what am I going to be integrating here? It's going to be 1 over u du. Is that okay, Blake? Yeah. No, I did a lot of stuff there. That's why I was pausing. And
Yeah, that makes sense.
okay. So again, that's just a natural log rule. So it'll be the natural log of u. And then I have my plus c tacked on. And then we're given some other information. We're told y of pi over 3 is equal to a. And x is bounded between 0 and pi over 2. Why do you suppose that we have that boundary for x given? Because we can't take an ln of a negative? Nope. Because even if I put something bigger than pi over 2 in there, I won't have a problem doing ln of it because there's really... Okay, so there's two reasons. I would say, one, here, what's tangent of pi over 2? undefined, right? That's an asymptote. And then what sine of something that's less than 0? Negatives, right? Like sine of negative pi over 2 is a negative value, right? So it's in two parts, you know. We can't equal pi over 2 because that's going to make the tangent undefined. And then we need to be between 0 and pi over 2 to make sure sine in our answer is a positive value. So I guess I was a little quick with the natural log being a problem, but we're taking the absolute value of it anyway, so it's less of a problem there. Okay. So let's go ahead and plug in some values then. So we have a, or natural log of absolute value, a plus a equals natural log absolute value sine pi over 3 plus c. Sine of pi over 3 is? The way I think about that, if sine is the y-coordinate, pi over 6 is the lower point, so that should be the 1/2. Sine of pi over 3 is higher. That should be the root 3 over 2. So c is going to be the natural log of 2a minus the natural log of root 3 over 2. And I dropped the absolute value there because root 3 over 2 is positive, so they don't really need it there. It's fine to leave it. And then probably they would do the quotient rule for logarithms, the quotient property, I should say, for logarithms. So that's going to be 2a times 2 over root 3. So we can say then the natural log of a plus y equals natural log of sine x plus natural log 4a over root 3. And we probably want to get, I'm guessing the book gave you an answer with y by itself, because that's perfectly doable for us. So let's go ahead and compress those two logarithms with the multiplication property of logs. And then we can do like exponent base e to both sides. And then we can just subtract a from both sides. And that, I'm guessing, is probably what was in the back of the book. Let's look real quick, huh? All that log stuff, you know, comes back with a vengeance. Let's see, 9,317. Yes! That is it.
The one question that I do have, though, is that since a is a constant, right?
Mm-hmm.
But it could be any constant.
Mm-hmm.
So then why would we have to put c in?
Because c is the result of the integration.
Okay.
Right? So the a is like locked inside of that log. if I took the derivative of this, the c just gets blown up when I take the derivative. The a is going to stay when I take the derivative.
Okay, that makes sense.
Right? Mackenzie?
Why is it a
Because when I used the initial condition, I know that like x is pi over 3 and y is a. So I just put the y or a in for y.
Oh, okay.
Does that feel okay?
Yeah.
Again, good questions. Like we bulldozed through that kind of quickly. If we missed like the finer points there, like for sure, come back and ask. Totally a good idea. Robbie?
Did you do number 1?
Yeah, sure. So this is going to be basically the same process as the previous one, but we're not given initial condition for any of these. So it actually makes it like a little bit easier because there's less to do at the end. So the first step here is just to get the things separated. X is on one side, y is on the other. So I'll divide both sides by y squared and then multiply both sides by dx. We'll integrate both sides. I'm going to think of y squared as y to the negative 2. So when I do the antiderivative on that side, end up with y to the negative 1 divided by negative 1. And the antiderivative of x is just going to be x squared over 2. And I have my plus c. So that's going to be like negative 1 over y equals x squared over 2 plus c. And we can push the negative sign over. And here's the thing. I don't really need to change the negative sign on the c. It's okay if you do. But since it's an arbitrary constant, if it's negative, if it's subtraction, I can just think about plus the negative of the constant. So let's just call it c, so it's fine. And then what we'll need to do to get the y by itself is we'll just do like the reciprocal of both sides. So probably, let's think about it with a common denominator. Probably something like that, and then again, you can just drop that to a single c. And I think that should do it. Would be my suspicion as it's written something like that. Yeah. Yep. I mean, I think they used the letter K for their constant when they took the 2c and turned it back into a c, but like, you know, whatevs. C is C is C. Mackenzie? 9 on the same section? Okay, no problem. It was just a little bit mumbly. I just wanted to make sure I was doing the right problem before. All right, so we have dp dt equals t squared p minus p plus t squared minus 1. Okay? So the trick is going to be separating this, right? What I'm going to notice here is how many terms do I have in this polynomial on the right-hand side? I have 4 terms. That's right. So I'm going to try to factor this. What's the method that I would use to factor a 4-term polynomial? Grouping. So I'm just going to make 2 groups. From the first group, I can take out a greatest common factor of p. And from the second group, I can take out just a 1. So that's going to be p plus 1 times t squared minus 1. And now I'm real happy because I notice that when I do that, I have a factor of p times a factor of t. And there's no shared variables in between the terms, which is awesome. So I'll divide both sides by by p plus 1, and then multiply dt to both sides. And that'll separate things. We'll integrate both sides. Again, this is like a little itty bitty baby u sub here. It's okay. That's okay. It would not, would be the question you're asking, but you saw it before you finished, so you're good. So we have the natural log of p plus 1, or absolute value p plus 1. And here, this is just, I can integrate term by term. So it's going to be t cubed over 3 minus t plus c. And again, I can get, this is separable. The p is just in one place. I should be able to get the p by itself to write my equation. So I'll do exponent base e to both sides. And since this is like an exponential over here, I know that an exponential is always positive, so I can drop the absolute value here. And then we'll just subtract that 1 over. And they probably in the back of the book took care of that to write it as a constant. So they probably wrote it as like e to the c times e to the t cubed over 3 minus t minus 1, and then just called that like a constant. Would be my expectation of how they would have ended up writing that. Does that feel okay, Mackenzie? Now, why did they, in the answer key, they used a plus or minus, but you shouldn't need a plus or minus there. Any power of e is positive, right?
Yeah, that's right.
Anyways, well, apparently in the text they used that, and then they stuck a plus or minus here, and now that just gets absorbed with this to call it a C. But details matter, so let's be specific. I don't want to give you a short change on that. Oh, I'm dumb. Of course I still need it. Here's the reason. Is p plus 1 can be negative, right? Now it's always going to equal something positive. But like, that's okay. Yeah, so that's why the plus or minus needs to be there, is because the thing inside the absolute value can be negative. So I still need to do the plus or minus, but it didn't affect the final answer. Blake?
Would you mind doing number 22 in the same section?
22? Sure. I need some space down here or something. That's little now. So it says solve the differential equation, yada, 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 by making the change of variable v is equal to y over x.
Did we learn about what the change of variable was in the notes?
No. So let's just kind of keep that in mind, that eventually we're going to probably need to make that substitution. So I suppose I would start by dividing both sides by x. And I guess so let's write that y prime as dy dx at this point. Okay. All right. So let's think for a moment. So we have this. Feel pretty good about that. Now is going to come in time for this substitution that they're asking us to do. So I think eventually I'm going to want to get like a, write this all in terms of v's and x's, or, yeah, probably v's and x's, since I know that like vx is also y. So if I took the derivative of both sides of this with respect to x, let's say, write it that way. So that would give me a dy dx on the left-hand side, right? But to do the right-hand side, what am I going to need to use? Product rule. So I have v, and then the derivative of x is just 1, plus x, and the derivative of v with respect to x gives me the differential dv dx. So if I take this piece, I can make a substitution here. And if I use this, I can make a substitution here and here. And now I think I can separate things, right? So if I subtract v from both sides, and now we're good. So I can divide both sides by x, and then divide both sides by EV, and multiply both sides by dx. And now we can integrate. What's the antiderivative of 1 over e to the v?
You have to do something.
I would just think about it as like e to the negative v. So that's just, so the antiderivative of that is just going to be negative e to the negative v.
We can do that.
Sure.
Oh.
Yeah, why not? And then we have natural log of x, or absolute value x, plus c. So I'll move the negative sign over to the other side. And then,
Okay, how'd you get rid of the negative on the b?
oh, I shouldn't have. It should still be there. Apologies. Thank you. And then we'll do the natural log of both sides. Why is it okay to take the natural log of negative natural log absolute value x plus c? How do I know that's not going to be negative? Well, it might, but you got that plus c at there. That'll probably take care of it. Or if this to be a viable solution, it's going to take care of it. Then we multiply through by the negative. And then we plug back in that v was y over x. And then we multiply both sides by x, and I'd say we're donezos here. Yeah, that's what they did. So the trickiest piece was like, how was I going to use that change of variable? Because without that hint that they gave us, what we had wasn't going to be separable, right? There's not going to be a way to separate the x and y's out of there because you have the stuck in the exponent and also not in the exponent. So like, how do I get it out of the exponent of e to the y over x? There's nothing I can do to get it out of there. I had to do this other tricky mumbo jumbo. And thankfully they gave me a hint as like, here's the tricky mumbo jumbo that you need to do. All right. Last call here. Cool. It's a good block of questions here, guys. We're going to save 9.4, I think, for next time. I want to do 9.5 today, given that we just spent a half an hour or whatever burning through some questions. 9.5 is a little more straightforward in terms of what I have to show you guys to be able to do this. So I'd like to start there, because I think that'll be a little bit easier to kind of do in the class time we have remaining. Okay, so we're going to talk about a new type of differential equation that's not separable the way it's currently posed to us. So this is, these are called a first order linear differential equation, where you can write it as you have like your y prime, some function of x times a regular y variable equals some function of q, or some function of x, a different function of x. So, for example, something like this we can make into that linear form, right? So what am I going to have to do to get this equation that I've written into the linear form above? So I need the y prime by itself, right? So what should I do? Divide by x. So I have the y prime by itself. That's good. I have a function of x times a function of y equals some function of q, or some function of x, some other function of x. And that other function of x can be a constant. That's fine. Everybody's okay so far of how I've rearranged that to get it into the form? Now, this, again, not separable, right? However, what I might have noticed here is that perhaps this part right here could that be the result of some product rule?
Yeah.
Certainly looks like it might be, right? So the question is then, how do I smush that back together and figure out what product rule it was? Right? All right, so skip through that. So what we're going to do is we're going to multiply both sides of our first order linear differential equation by some function I of x. We call that function the integrating factor. And we're going to pick that function I of x such that I of x times the left-hand side is just the derivative of I of x times y. So if I do that, I can multiply both sides by I of x. That result is I of x times y, or the derivative of I of x times y. And now I can just integrate both sides without a problem because I have the derivative around one thing, and then the other side is all in terms of x's. John?
Why is the derivative, like in that last step there, we're also deriving the I of x. It's not like I of x times y prime.
Correct. So what we've done is this piece here, when we found our I of x, which we haven't talked about how to do that yet, but when we do, that I of x is going to be such that the left-hand side is the result of a product rule derivative of I of x times y. So that's the derivative of that product rule. And that's what the notation there is saying. Is that?
Yeah.
When we go through and do it by hand with a specific function, it'll become a little bit more clear. We're just kind of like outlining how this is going to work right now and why it's going to work. Okay. So blah, 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 blah. All right, so how do we get this I of x? So we have this, we have our first order differential equation that we've multiplied both sides by I of x, where I of x needs to give us this relationship, right? That's what we need I of x to satisfy, is that the product rule derivative of I of x times y is I of x times the derivative of y plus p of x times I of x times y. Right, because all we're doing here is just distributing that through to get this. And this is just the derivative, product rule derivative of I of x times y. So if I notice here, this piece can cancel from both sides. That's great. And if I look at this again, the y's can cancel. And what I have is this, which is specifically like a separable differential equation. So I have p of x times 1 over I of x times the derivative of I of x. I integrate both sides. And yada, yada, yada. What do I get? That integral of p of x d of x, or p of x dx is 1 over I, or the natural log of I, excuse me. So drum roll here. I is going to be some constant times the e to the integral of p of x dx. So that is our formula for that integrating factor I. It's just going to be e to the integral of p of x dx, which is quite a relief that it was an easy thing to remember, right? Let's put this into practice. So if I look at this, this is already in the linear form. Where I have y prime plus a function of x times y equals some other function of x. Everybody agree that it's in the form that we need it to be in? So we'll calculate I of x. That's equal to e to the integral of px dx, which is e to the integral 3x squared dx, which is just e to the x cubed we don't need to do the plus c's. It'll be fine without it. It'll end up like absorbing the plus c at the end. So we can get away without having to worry about that, and it makes all the algebra like way cleaner if we do that. So now what we do is we take our I of x and we multiply it by both sides of our linear equation. I'm writing way more than I in all rights need to, just to kind of remind you of what's going on. Oops. Now this piece just becomes the derivative of I of x times y and this is just I of x times q of x. Everybody's okay with that? Now we've done it, separated it enough that we can integrate both sides. I know from the fundamental rule of calculus that the integral of a derivative is just that function back again. Everybody's okay with that? And then to integrate 6x squared e to the x cubed, what am I going to need to use? How am I going to integrate that? I don't actually need to do integration by parts here. I can do u sub with this. What is the u?
X cubed.
Yeah, if the u is x cubed, du is going to be 3x squared dx. So I'm just going to like do one of those. Everybody's okay with kind of seeing that? So I have my 2, and the integral of e to the u du is just e to the u. And then we have our plus c, right? What? Well, that's part of the du, right?
Oh, yeah.
So that just gets sucked up into the du, and we just have e to the u du that we're integrating, or the integral of e to the u du. Is that okay? All right. We're just getting the y by itself, so I'll divide both sides by e to the x cubed. And I am donezoed. Huh? It's okay?
How would you able to take the
I divided both sides by e to the x cubed to get the y by itself. So it just canceled off the 2. Yep, exactly right. Exactly right. The reason I wanted to do 9-5 today is this is really the only skill in here, is just doing these solving these differential equations using this integrating factor. So like, this is the skill for this lesson. So we're just going to do a couple more practices with that. Do you guys want to take a stab trying this one on your own for a minute and then go through it? Okay. I think I got 2 more here to do this one and another one. So if you want to try this one, we can go through it, or if you wanted to watch another one before we do that, either would have been fine. I am flexible. See? I touch my toes. Everybody makes a big deal about not being able to touch their toes. I don't get it. It's pretty easy. That would have made a great Greek hero. Reminds me of the story where, who was it? It was like Odysseus who's challenged Hercules to like a discus throwing contest. Or they're on the beach or whatever, and Hercules bombs something way down the beach, like impossibly far. And Odysseus turns and faces the ocean and throws the discus into the ocean and just skips, it skips, it skips, it skips.
It's pretty smart.
Yeah. It's cheating, like the touching your toes thing. It's like, you didn't specify how we need to do this, just that we needed to do this. you're stuck or you're concerned about how things are going, I wrote up a little bit, a couple of first steps here. If you don't get the integrating factor right, there's not a whole lot you can do with this. So once we have I of x, we know the left-hand side is just going to be the derivative of I of x times y. The right-hand side will just be I of x times the q of x. Or just the right-hand side. I guess I don't really need the absolute values there. Yeah.
I got to the last step and was like, I do not know how to integrate that. I do not know how to integrate that.
It's okay. That's why we do them, right?
Yeah.
Again, what if I said over and over and over again? The hard part of calculus isn't the calculus part, it's the algebra part. You guys want to try the next one? I'll do the same thing and just kind of periodically put some work in. So as you're doing things, you can refer back and check. How many of you are stuck at this point? What do you think we do? Can we do that integral e to the x squared dx? Right. So you can't integrate it by parts because they're not two functions. So that's out. Can't u sub it because obviously you probably tried every possible value for u. There's like either x or x. I mean, it's really just x squared is the only thing you could do, right? But that doesn't work. So, you know what we do? This needs to be as a function of x, right? I remember the fundamental rule of calculus, where I can just rewrite that now as a function, an integral as a function of x, and I'm done. It's done. Just cheated, just left the integral in there. It's okay. And I suspect even if you had like put this piece here, that'd probably still be okay. I like it a little bit better because you're connecting it back to that fundamental theorem of calculus, part A, in the beginning, by writing it as like a function of x, where x is a input in a definite integral. But I don't think it would be wrong to leave it just as the indefinite integral of e to the x squared dx. So the takeaway here, guys, on the homework in this section 9.5, you may have answers with integrals still left to know. That's okay. It's okay. That was the point in doing that last one. It's just that, let's see an example where this happens. It's okay. What do you guys think? This section, not too bad. Nothing in chapter 9 has been like brutally difficult, right? It's been tricky at points. And like you have to really kind of remember all of the skills kind of come together here, because you're using derivatives, or integrals, and like remembering the relationships, and the algebra comes in. You're having to like it all convalesces here as one but the symbol pushing is usually not too bad. Doesn't get like brutally complicated. So that's 9.5. We're going to do 9.4 next time. That'll be it for chapter 9. So we'll probably do a review day next week and then take the test, chapter 9 test, which will put us on track for review here for the rest of the couple last days of March and then into April before the exam. Once we get into this review period, my main, or the way class will be formatted is we'll do some like practice multiple choice questions. We'll probably do it like with some partners as like a little bit of a contest here and there. We'll do somewhere just like I give you, ask you to do like one of the progress checks from a chapter, or maybe even just give you like an old multiple choice section from a previous AP exam. We'll just do it timed and see how we do. And then we'll give you some free response stuff that we'll ask you to take home, come back, and we'll write them on the board and talk, or write it, or have you take a screenshot and email it to me, and I'll just go through them on the board and talk about like scoring wise how I would score this if I was pretending to be an AP grader, and where silly things that would have cost you points, or things that would have been easy to show that would have picked up points, to really kind of try to coach us up a little bit on getting used to the time, and then like what are the things that when somebody's grading one of these things, what do they look for, and what are the what are easy ways to lose points or easy ways to pick up points. So that's the plan here for the last month or so of class. Along with that, I'd probably like to sprinkle in here or there like 2 or 3 other topics. We'll probably just do those as like half of a class. We do some of these other topics, and we'll do some practice after that. Nothing after the chapter 9 test other than homeworks, though. Would be, well, I would have okay, fair question. You'll definitely have like an integration by parts problem and a partial fraction decomposition problem. But I'll tell you specifically in the question, like, use integration by parts to do this. Use partial fraction decomposition to do this. So, and then I think after that, I tried hard not to have any non-AB techniques pop up in any of the other problems. So I don't think that you need, as I was writing this, I'm almost done. I'm still proofreading. I have one question that's kind of messed up, that's not working the way I wanted it to, that I have to go back to the drawing board on. But otherwise, all the other questions that I wrote, I think, are good. But that's, so that, yeah, Mackenzie, I guess there would be a little bit of Chapter 7 stuff. But most of Chapter 7 is non-AB topics, so I've kind of tried to keep a light version of that. You know what I mean? We actually did one in the examples. We did or the questions you guys asked, where did that go? Right here. That's actually not an AB technique that we just kind of made up on the fly. Where I used U sub to do that trigonometric integration. I don't think that that's technically an AB topic. I'd have to go back and really look closely, but I don't think it was.
So what would it be then?
Yeah, I think it'd be a BC topic, to be honest with you. Because some of those get like brutally difficult. That was a pretty easy one, where I didn't feel bad about like dropping that in. It's like, it's just a U sub. It'd be fine. You have to do like, you have to use an identity. But I figured you guys would be okay with that. It was a basic identity. It wasn't like, okay, you need the half angle formula, this version, and like, no. It's just like your basic reciprocal and quotient identities is all we use there. So I figured that was going to be okay. In fact, if I didn't tell you, nobody would have even thought different. Been like, yeah, I should know how to do all that. Just probably what you all thought when we did it. It's like, okay, yeah, I need to know those identities. That's true. I should know that. Okay, just a U sub after that. Okay, I know how to do that. But, yeah, so what do you guys think? It's getting right down to the end of it here, which is pretty exciting.
Yeah.
It'll feel good to like know that at least for my AP calculus class, like the grade part is now going to be kind of done, right? We'll still have some homework and some participation stuff, but like I don't imagine the homework is going to be more than like one section a week, which sounds pretty righteous, and then some stuff to do in class or whatever, So that feels pretty good. You know what I'm saying?